Okay, welcome to our last notes for our circuits unit. We're going to be talking about power today. We remember power from our work and energy unit. Power, let's get our pen set up here, power, and we use P to stand for power sometimes. I'll tend to write it out just because I don't want to get it mixed up with anything else. But power is simply a change in energy over time. Sometimes I leave out the delta T there because it's kind of implied, so we can get rid of that if we don't want it there. Okay, but power, then we know, is just a change in energy over time. And this is just from our work and energy unit that we had first semester. So a little bit of a review, okay? Our units for power, then, just like energy, joules, and time is in seconds, so our units were joules per second. Now, we had a special name for that. We called it a watt, but let's leave that out for right now. We're going to bring the watt back in, but let's leave that out for right now, okay? Then let's take a look at some of our other units that we have from our circuits unit. So we've talked a lot about electric potential difference, V, and we said V is just energy per charge. So our units for electric potential difference is just a joule per a coulomb. Well, that looks really similar to power, but it's not quite right? A second is not a coulomb. You can't say an apple is an orange just because they're both fruit. So they're close, but not quite, okay? Our next one that we talked a lot about in this unit is current. Well, current, we know, is just a quantity of charge that passes by a point in a given amount of time. And our units for current, charge we measured in coulombs, and time, of course, we measure in seconds. Well, that's pretty close to power, right? We have the right units on the bottom. We just have the wrong units on the top because the units that we want are joules per second. But notice, we can do something kind of interesting here. If we take a joule per coulomb, which is just electric potential, and we multiply that by a coulomb per second, which is just current, we end up with, because these coulombs cancel, we end up with a joule per second, which is exactly the units we want for power. So it turns out that power is just electric potential times current. Now, something else that we know from this unit is voltage is just current times resistance. So I could plug in I times R for this V, and I would see that power is also equal to I times R, which is just I squared times R. Something else I could do, because I know that voltage is current times resistance, is I could say, well, current is just electric potential divided by resistance. So I could plug that in to my power equation, and I could say that power is also electric potential squared divided by R. So we have three equations for power, and which one you use will depend upon what you're given. The first is that power is equal to V times I. The second is that power is equal to I squared times R. And the third is that power is equal to V squared divided by R. You can derive these second two anytime you need to just by knowing Ohm's law. So we want to make sure we keep these in our mind. And we're going to use these, and we're going to see what these mean kind of in everyday usage, okay? Now, if at any point you've gone to the hardware store and you've had to buy a light bulb, you've probably been inundated with a number of ratings of light bulbs. There's all kinds of ratings, and they're all based on what the hardware store will call wattage. And we remember a watt, and I know we didn't use a watt in our first discussion here, but let's bring that back in. Oh, I don't like that color. Let's go ahead and bring that back in, and let's recall that 1 watt is simply 1 joule per second. So it's a unit for power. And these are the standard units for power. We normally hear of watt for power. Now, I don't like saying a bulb's wattage because it's like saying a person's meters, right? It kind of indicates a height, but it's not really clear. So we're going to say the power of a light bulb, but when we say that, we know that it's going to be measured in watts, and that 1 watt is simply 1 joule of electric potential energy. So let's write this out. So 1 watt simply means 1 joule of electric potential energy is converted into something else. And for a light bulb is converted into usually light, ideally, and thermal energy each second. So every second for a 1 watt light bulb, 1 joule of electric potential energy is converted into heat and light. So for a 100 watt light bulb, in every second, 100 joules of electric potential energy is converted into heat and light. Okay, so we're getting somewhere. So now we need to talk about when we plug items in, because a lot of what we're going to do with the last part of this unit is to look at, well, how much current are we getting from the power company? So ComEd, Commonwealth Edison, is the power company that provides all of our power and energy needs in this area. And what we're going to see is that we've been talking a lot about 9-volt batteries or 12-volt batteries or 1.5-volt batteries, but the electric potential difference delivered by the power company is supposed to be 120 volts. Now, this is in the U.S. If you go to other countries, for instance, in many countries in Europe, you're looking at 220 volts. And this is just because when the electric supplies were starting to be built in different parts of the world, people decided that different amounts were better for whatever reason. There was nothing standardized. Now in the US, we've standardized to 120 volts. Europe, many countries in Europe have standardized to 220 volts. That's why if you travel with your iPhone and your power plug and you go to someplace in Europe, you have to have an adapter. Otherwise, you won't be able to charge your phone. Gasp. Disaster. Okay. All right, so how are we going to use this? What good is all of this? All right, so really our goal is to figure out, well, how much current is being pulled by a 100 watt light bulb or anything that we're going to plug into a wall outlet. And the reason we want to know that is a very practical reason that we're going to get to towards the end of these notes. Okay, so stay with me. Our goal basically is to figure out are we safe by plugging in the amount of devices we have currently plugged in, or are we potentially creating an unsafe situation if we plug in too many devices, okay? So let's take a look at what we got here. How much current does a 100 watt light bulb draw when plugged into a wall outlet? Well, we have our equation. P is equal to I times V. It's the same thing. P is equal to VI. Sometimes I write it one way, sometimes I write it another way. And we know a couple things. If it's a 100 watt light bulb, we know the power is 100 watts. And we're assuming, unless told otherwise, that we're in the United States. So we know that the voltage is 120 volts. So the electric potential difference is 120 volts. So I can use my equation. I can plug in and I can say, well, 100 watts is equal to 120 volts times the current. You're going to need your calculator. Go ahead and get your calculator out. Figure out what the current is for that light bulb. I'll wait. You can hit pause. Okay, I'm back. The current then is 0.83 amps. That's a decent amount of current. Okay? So I plug in one bulb, and that bulb pulls 0.83 amps from ComEd. Let's take a look now what happens if we set up 2 light bulbs. Okay? If we set up 2 light bulbs in the same, and we're going to use a parallel circuit. Okay? Why do we use a parallel circuit? Well, think back. If I have one light bulb here and I want it to stay on and I don't want the brightness to dim, I need to make sure that the second light bulb is connected in parallel, or the first light bulb will dim, and that doesn't do me any good. I don't want that happening. So the circuits in your house are going to all be wired in parallel so that you don't have to run your refrigerator just for your microwave to work, or vice versa, and so that your lights will have the same brightness regardless of how many are turned on. Okay, so in parallel, we know that bulb 1, the current is going to be 0.83 amps. For bulb 2, we're going to have to pull the exact same current to get that guy to go on. But then we also are turning on a 650 watt toaster. So we have to figure out the current that the toaster is going to draw. So we're just going to use P is equal to I times V. And 650 watts is equal to the current times 120 volts, the electric potential difference. Better get that calculator out again, figure out what that current is. I'll wait. Okay, hopefully you found that the current was 5.42 amps. So now we've got the toaster current is equal to 5.42 amps. So now we need to find the total current, and we do that simply by adding up all of these individual currents. Go ahead, put that in your calculator. I'll wait. Did you get your total current to be 7.08 amps? That's what I got as well. Okay. Now, let's first talk about, before we get to anything else, let's talk about how you pay for electricity from the power company. And then we'll get to how we stay and how we keep our circuits safe in our home. So the price you pay to the power company is based on the energy used. It's not based on the power. Bigger institutions like the school, they will get a bill based on the power, because the electric company has to gear up so many generators if they need a lot of energy quickly. But for smaller users like a home or a small apartment building or your condo or whatever, you're only going to pay for the energy you use. So whether you use all the energy in one day or all the energy spread out over multiple days, it's not going to matter to your bill. Okay. Now remember that power, right, is just change in energy or over time. Well, that means that energy is just power times time. Now, the electric company doesn't like to use joules for energy. They say, well, energy is power times time. So we're going to say that that's going to be power in, right, we use watts times we use seconds. Now, the power company doesn't like watts because it's too small for them. So they like kilowatts. And seconds are not convenient for them either. So they use hours. So they're going to measure their energy in kWh. That just means kilowatt hours. So the kilowatt is the power, and the hours is the time, and we know power times time is the energy. All right, so we are to the point now where we want to go ahead and we want to use that idea, and we want to figure out, well, for any given component, any given light bulb in my house, can I figure out how much that's going to cost if I say run it for 24 hours a day for an entire year? So at some point you probably heard a parent tell you, turn the light bulbs off, the electric is expensive. Let's figure out exactly how expensive it is, okay? So let's assume that we have a 100-watt light bulb. It stays on 24 hours per day, and you want to see how much that's going to cost you per year. A typical price from the power company is about 10 cents per kilowatt hour. That means 10 cents, that's $0.1 per kilowatt hour. These problems are easiest to do if you think of them as a conversion problem. So remember back in the beginning of the year, we would convert miles per hour into meters per second. The process we're going to use for these problems is basically the same. So if we want to figure out how much it costs, we're going to treat this as a conversion problem because we really want to turn 100 watts into dollars per year. There goes my dog again. Okay, so we're going to start our conversion problem the way we start every conversion problem by writing what we know. We know we have a 100-watt light bulb. But we also know that we're going to have to convert that 100 watts into kilowatts because our price for the energy is given in kilowatts. So the first thing I'm going to do for my conversion then is put my little multiply and my line, and I know that there are 1,000 watts in 1 kilowatt. Then I can see that the watts cancel with watts, and I'm left with kilowatts. And then there's different ways you can do this, but I'm going to go ahead and I'm going to multiply by the price. And I'm going to say it's 10 cents or $0.1 per kilowatt hour. And I could see then that this kilowatt cancels with this kilowatts, and I'm left with dollars per hour, which would be great if that's what I wanted to know. But I don't want to know that. I want to know the dollars for an entire year. So I need another conversion that gets me from hours to years. Well, that's a tougher conversion, but I do happen to know a conversion for hours to days. And since I'm doing this 24 hours per day, I can put 24 hours in 1 day. And then I see that the hours cancels with the hours. Now I'm left with dollars per day. But I finally also know that there are 365 days in 1 year. So I can see that the days cancel with the days. The only thing I'm left with then, the unit on the top I'm left with is dollars. The unit on the bottom I'm left with is years. So the rest is just a calculator problem. So to plug this into my calculator, I'm going to go ahead and multiply anything on the top. So I'm going to put 100 times 1, but I don't need to multiply by 1. So I'm going to put 100 times 0.1 times 24 times 365. And then I'm going to divide by anything on the bottom. The only thing on the bottom besides 1 is 1,000. So I'm going to divide the whole thing by 1,000. So go ahead now, get your calculator out, and see what you get so that you can check and make sure you got the same thing that I got. All right, hopefully you got $87.60 per year to operate that one light bulb. So maybe that seems like a lot, maybe that seems like a little, but I can tell you what, to your parents, it's a lot. You don't want to waste that, so, turn those lights off, okay? All right, let's try another example. This time, we've got a toaster, and it's a 575 watt toaster that we use for 10 minutes per day, every day of the year. And we want to go ahead and we want to find out how much does that cost us to operate. And since the problem doesn't tell us, let's just assume the same energy cost from above, and let's just assume that it's 10 cents or $0.1 per kilowatt hour. So we're going to start this problem the same way we did the last one, where we're going to say, okay, we've got 575 watts. Well, I know my energy cost is 10 cents per kilowatt hour, so I better convert those watts into kilowatts. So I'm going to go ahead and I remember that there's 1,000 watts in 1 kilowatt. And then I'm going to go ahead and put my energy cost, and I know that it was $0.10 per kilowatt hour. And I know I'm using this this item for 10 minutes per day. So in an hours, I need to get that hours there. So I see that the watts cancel with the watts and the kilowatts cancel with the kilowatts, but I need to get rid of those hours and put that into minutes. So I happen to know that in 1 hour, there's 60 minutes, but I'm only using this device 10 minutes per day. So that's a little different than we had before, okay? So I can see that my hour cancels with the hour there, my minute cancels with the minute. So far I have dollars per day, but I know that since I'm using this toaster every day of the year, I can say, well, 365 days I'm using this toaster per year. No vacation for the toaster. And then I can see that the day cancels with the day. I'm left with dollars on top, year on bottom, which is exactly what I wanted. So I can go ahead. This is now a calculator problem, just like it was before. So anything on the top gets multiplied, 575 by 0.1 by 10 by 365, multiply all those together. And then I'm divide that by 1,000 and divide it again by 60. So go ahead and try that now and let me know if you get the same thing I do. All right, hopefully you got that operating this toaster every day for 10 minutes a day per year is $3.50 per year. Okay, at the beginning of the notes, we said that the goal of understanding power was first to figure out how much current we're pulling in the house to see if it's safe. The secondary goal was to also figure out how much it costs to operate different devices. So let's go ahead and let's take a look at some of the safety devices. And let's talk about their purpose. So most safety devices, most electric safety devices in a house have one of two purposes. One is there to protect the house, protect the wiring in the house. So all wiring is made of some kind of conductive material, usually copper. And around that copper is usually a plastic or rubber coating, because obviously we can't have one copper wire touching electrically and conducting to another wire unless we want that to happen. So we insulate, what's called insulation. We put insulation around the wires so that the current can safely flow through the wire and not jump into other places that we don't want it to just by mistake because it touches something that it shouldn't. Okay, so one goal is to keep those wires safe, because if they get too much current, they will get too hot. And once they get too hot, the conductor part of it gets too hot, it could burn off the insulating coating. If that coating goes, now we can start getting short circuits that we talked about in a previous note sheet. And once we get short circuits, we're pulling lots of current, and now you start getting things heating up and you can cause a fire. So some safety devices are designed to make sure that that doesn't happen. Other safety devices are designed to make sure that the people, the occupants, don't get hurt by mistake. So we're going to talk about both of those, okay? Now, the first that we're going to talk about, first safety device we're going to talk about is a fuse. And fuses were pretty common. You still see fuses in different components and different electrical devices. You see them in your car. There's a fuse box in your car. You don't see them too often in houses anymore, but every now and then you might see one. So a fuse is designed to protect the wires from melting and starting a house fire. Okay, so their job is to protect the wires from overheating and starting a fire. So a fuse is a small metal wire that melts. So it's a small metal wire that melts. And it's designed to melt at a lower temperature and a lower current than the insulation of the wires. So it's going to melt before the house wire's insulation. So it's going to be the first to fail. The reason that's good is because if that fails, the wires in your house will not fail. Okay? So once the fuse is burned out, that's it, it's trash. You have to throw it away. Okay? It's no good anymore. You can't fix it. There's nothing you can do. It just gets tossed, and you have to replace the fuse with another fuse. And fuses have different ratings. Some can withstand 5 amps. Some can withstand 10 amps. There's all kinds of different rated fuses depending on the application. Now, the problem with a fuse, and the reason they're not used very often in houses anymore, is because they are easily replaced by a stack of, say, pennies. So imagine this, it's the middle of the night, the fuse blows because somebody got up and used a hairdryer when they weren't supposed to and pulled a bunch of current with the microwave running. Now the fuse blows. Well, it's the middle of the night, you can't find the fuses, so what do? You grab a stack of pennies and you put them where the fuse should go. That solves the problem of current flowing through that circuit. Current will now flow through that penny that stack of pennies very easily, and now you don't have to worry about the fuse blowing. The problem is what happens if you forget to then replace the fuse and you leave the pennies in there. Now you've just very easily taken out the best protection you have against an electrical fire in your house. So these aren't used very often anymore, especially in locations where they're easily replaced by people who, don't mean to take out the safety device, but just things happen, okay? So instead, most fuses in homes have been replaced by circuit breakers. Circuit breakers are also designed to protect against house fires or against pulling too much current. They just work a little bit differently. So they don't have something that melts. they have an electromagnet that trips or flips a switch once a large enough current is reached. Okay, so very similar to a fuse, circuit breakers have different ratings, 5 amps, 10 amps, 20 amps. And once that current is reached, the circuit breaker will trip. And what that means is that a switch in the circuit breaker will open so that current can no longer flow. Now, if the problem persists, because sometimes you'll have a circuit breaker that just, you reset it. So let's put that in our notes. In fact, we can reset a circuit breaker once it does trip. And it's pretty easy. If you've ever seen the circuit box in your house, it's just, you just push it one way and push it the other way, and then poof, it's back to its normal position. They're very easy to reset, and then you can continue using the circuit as you had before. Now, it doesn't address the root cause of why the breaker tripped. You have to do that on your own, but once it's fixed, then you don't have to replace anything. And the other nice part is that it's very, very hard to remove, so you're not just going to remove that and replace it with a stack of pennies or a wire, okay? So again, fuses, circuit breakers, designed to protect the wires from pulling too much current, because once they do pull too much current, the wires can overheat, the insulation can melt, and now you have a serious problem in the house and you might not even know it, okay? The next two things we're going to talk about are designed to protect you. So grounded plugs, and you've probably seen these. You've probably seen plugs that are 2 prongs, and that's a hot and a neutral. And then you've seen three prongs. That's the hot, the neutral, and the ground. Okay, so the ground plug protects the users so that you don't get hurt. So for example, let's say you have a refrigerator and it's a 3-prong plug. Okay, one we said was the hot, one we said was the neutral, and one we said was the ground. Now the hot is the wire that comes from the utility. Okay, so that's why we call it hot, because that's carrying the energy from the utility. The neutral just goes back to the utility, right? For every circuit, you have to have a complete circle. So one wire coming from the utility, one wire going back to the utility. So the hot comes from the utility, the neutral goes back to the utility. The ground wire simply connects a, for instance, the device. So for instance, a refrigerator. So the ground connects the refrigerator metal. So the actual metal part of the refrigerator connects the refrigerator, the metal box, to the actual ground. So we talked about grounding in our electrostatics unit, and there's a wire, and many times it's green, and it goes right to a metal post that's dug somewhere in the backyard. So in the 3-prong plug, the 3rd prong of the wall, the 3rd part of the receptor in the wall, there's a wire in there that goes right to the ground. Now, why do we do this? Okay, so you've got your hot wire for the refrigerator, and if that breaks and it accidentally touches the metal refrigerator box, that metal refrigerator box is now part of the circuit and it's charged. But you won't know it until you go to grab the refrigerator door and try and open the refrigerator door. Then you are part of the circuit. And now we know that that's a huge problem, because 120 volts with all of that current rushing through your heart could stop your heart. So the idea is to keep users from becoming part of the circuit. So how does the ground do this? Well, the ground wire goes right from the refrigerator box, the metal part, to the ground. So if the hot wire is supplying the current, that current will go right into the ground. It won't go to you because there's no resistance in that wire. You've got some resistance, so you're going to get very little of the current. Most of the current is going to go to the ground. So the current won't go through your heart, it'll go to the ground, and then that keeps you safe. Now the refrigerator won't work very well, but at least you'll know, but you will not be part of the circuit when you go to try and open the refrigerator, okay? So that's why we have those 3-prong plugs. The last safety device we're going to talk about are bathroom outlets, and these are often called GFCI, ground fault current interrupter. So ground fault current interrupter. I think I spelled that right, but I'm not confident. Okay. And this is designed to protect you. And here's how it works. This outlet senses the current on both the hot wire and the neutral wire. So it senses the current on the hot and the neutral. Now these should be the same. Okay, these should be the same because we know that if you have a series connection, that the current going into the outlet's got to be the current coming out of the outlet as well. Okay, so these currents should be the same. So when would be a situation when they wouldn't be the same? Well, they wouldn't be the same if the hot current is coming to the outlet, then going into you, and then going from you directly to ground because you're touching the ground, you're touching anything, okay? In that case, the current on the hot wire will not be the same as the current in the neutral wire. The GFCI senses this and stops all current from flowing. Okay, the current stops, so stops current from flowing if hot current isn't equal to neutral current. So that's why we keep those a lot of times in a bathroom, because if something, say your hair dryer, falls into the sink, all of a sudden you're going to get a lot of current going from the hot wire into the sink and then down to the ground through the plumbing, which we don't want. We want that current staying in the closed loop that it is designed to stay in. Okay? All right, that was a lot of notes today, guys. Very long, a lot of stuff to talk about. So if you need to rewatch the video, go ahead. Otherwise, have a great day.